In this video, I want to focus on actually balancing chemical reactions and then run through some of the other hints that we see for balancing reactions. Now, for a problem like this, which is the more difficult type, okay, what you have to do is you have to interpret your molecular formulas correctly before you can balance this thing properly. This is why we do nomenclature before balancing equations like this, because then what we can do is we can interpret this correctly. So lead is one of those post-transition elements. It can vary in charge, usually a +2 or +4. This is at a +2 state. Let's just see what that looks like. Acetate, okay, for our class you can look it up. It would be this. That's the acetate ion. And notice the charges here are not equal and opposite, so they cannot come together in a 1-to-1 ratio. Instead, I need 2 of these for every one of those. Remember, when you have one of these polyatomics and you have to show more than one, then you have to put a subscript on the outside of parentheses for that. The problem is telling me that they're aqueous solutions. That means that we would have an AQ tag there. Potassium iodide, I'm going to speed this one up a little bit. Potassium is a +1, iodine is -1, so they're going to come together in a 1-to-1 ratio. Again, aqueous. Lead iodine has that formula. Notice it tells us it's a solid. So one thing, you're looking at a precipitation reaction here. And then finally, potassium acetate. Since potassium is +1, acetate is -1, these are going to come together in a 1-to-1 ratio with the cation always in front. Now notice I had 2 acetates here, I only have 1 here. Remember, the ratio between the anion and the cation is due to the charges of what's being paired up. So you factor that in now as you balance the equation. So now we shift gears and now we want to change the front. If I just quickly run through this, notice a hint here, balance polyatomic ions as a unit, meaning the fact that acetate is acetate here and acetate is acetate here. So I don't want to break apart carbon, hydrogen, and oxygen separately. If you did that, could you balance the equation? You probably could, but it would be more painful than this. Taking inventory, 1 to 2 to 1 to 1. Let's do the same thing on this side, 1 to 2 to 1 to 1. So 1, 2, down here. Sometimes it just works out like this. There's not a lot to do here. Sometimes additional hints are used. I'm not worried about it here. I think it just muddied the water more than needed. What I would do is just find the first one that's different and fix it. How do I fix it? Well, I can't take away something here to get 1 here. Once I have the molecular formula correct in the equation, I don't want to change anything like that, okay? So the only thing I'm allowed to do is actually change that. So great, it fixes my acetate, but also changes my potassium. That's going to be okay, because now notice what? Here, I've got 2 potassiums, 2 iodines. Well, as it turns out, potassium and iodine showing up in the same compound over here. By putting the 2 there, it fixes both at one time. That is pretty typical, especially for double replacement reactions. 1 or 2 tweaks and 1 or 2 changes in the molar coefficients and everything should be coming together. If you keep having to go back and forth and you're like on step 6, probably what's happened is that you have made an error in this step and an error in your molecular formula. So if it doesn't wrap up within, let's say, 3 or 4 steps, especially these double replacement reactions, then go back and check your molecular formula, make sure they're correct. Here's another one. This is the same rule that we saw for combustion reactions. Let's rewrite this so we have a little more room. I'm going to just skip the phases just to save a little time. I'm really right just after the balancing of the reaction. If I take inventory, there's only 3 elements. Actually, let's pause for a second. Let's take account of this idea of this free element. Well, that in this case, actually 2 of them, oxygen and chlorine. They're both in their elemental state, so I'm going to balance oxygen and chlorine last here. Again, this is a hint. Sometimes it's great. Sometimes it feels like, why am I doing it this way? More often than not, by using this hint, it simplifies the balancing act just a little bit. So over here, it's a 1 to 1 to 2, and then here I got 2 hydrogens, 1 oxygen, 2 chlorines. And again, I've already applied my rule. I'm going to do hydrogen first. So I need 2 here. So yes, that does fix hydrogen. And actually, it just happens to fix chlorine, and that's great. And then I apply same kind of logic to oxygen. I need 2 in front there, times 2. So it balances oxygen, but then notice what happens, and this is not unusual, okay? In the process of balancing the oxygen here, I have also changed my hydrogen count. Let's fix that. I no longer have 2 when I put the 2 there. Now I have 4. Okay, so what do I have to do? Well, I need to, if I got 4 and I want 4 total hydrogens, that means I got to change this molar coefficient. Times 2 equals 4. And, well, that also messes up the chlorine. That's fine. Take care of the chlorine. Is there a way to do that? There sure is. A 2. So the final balance is a 4 to 1 to 2 to 2. Sometimes that just happens where you have to go back and forth a few times. Again, if you keep jumping back and forth, something's wrong. I will say this type of example for our class would be sort of the limit in terms of going back and forth to different elements. Okay. One reason why I threw it in here at the test review, so you can see one of the more confusing examples. I don't want to say complicated because the reaction itself is pretty simple. It's not like it's not, big molecules reacting with each other. And the last one I want to do is actually, this is an acid-base reaction that I talked about in a previous video in this test review group. So the balanced equation is already given to us, so that's nice. Now we're not going to mess with ionic equations here. We're going to focus on net ionic equations, and then also we'll wrap up with the spectator ion. Let me approach this answer 2 different ways. For all acid-base reactions in our class, it's going to look like this. Proton plus hydroxide is going to react to form water. The proton's coming from the acid, hydroxide's coming from the base. If you look back at that second video, that's the characteristic molecules for these 2 different reactions. Here's that slide. Acid always has these protons in front that will donate to something. Bases always have the hydroxide salts. Again, future classes, there'll be other types of bases, but for right now, it's always hydroxide salt. It makes sense that these are the 2 species that actually changes in the reaction. So if I go in here and I highlight, well, there's the proton, there's the hydroxide, there's the water. Well, to pick out the spectator ion, it's associated with the salts. Or I should say the ions in the salt that's left over. Spectator ions, they don't change in the reaction. They're switching sides, if you will. They're switching partners. But just to pick out one, I could say the same thing about bromine or bromide. Calcium aqueous. It starts off as a calcium cation suspended in water, and it ends as a calcium ion suspended in water. It doesn't change. That's why we refer to these as the spectator ions. That's it. Thanks.